This video is going to cover the concept of molecular geometry. So in our last video, we learned how to look at a formula and draw what's called a Lewis structure, how these atoms within those different covalent molecules would be bonded together. In today's video, we are going to look at the different shapes that could result in those molecules. So before we get too far into what those shapes are, we have to learn about what's really causing those shapes to occur. And the thing that's causing it to occur is this idea called the valence shell electron pair repulsion theory. And you'll often see this abbreviated to VSEPR, or VSEPR. And in this idea, this explains why molecules and polyatomic ions are not flat structures. Everything is going to be three-dimensional. And even though we draw it kind of flat on our pieces of paper, that's not how they're actually appearing in nature. It's just difficult for us to draw them as 3D structures. And because they have 3D structures, it's the three-dimensional arrangement of those atoms that really helps account for the chemical and physical properties that we see of different compounds. So there are a couple of different models used to predict and describe the geometries for different chemical species. The one that we're focusing on in this class, again, is going to be this valence shell electron pair repulsion theory. And what that's talking about, if you think about the name, is simply the valence electrons within the molecule are going to orient themselves. They're going to position themselves. That's what that word means, to orient. So they're going to position themselves in order to minimize repulsive forces between electrons. So we have to remember that all electrons are negatively charged. And like charges, like or same charges, repel one another. So in these structures that we're going to be looking at, the electron pairs are going to position themselves so that they are repelling one another. And what an area of electron concentration is known as, what we're going to be referring to it as in this video, is this idea of an electron domain. So just an area, like it says, an area of electron concentration. Another way of thinking about it is an area where electrons could be found in the molecule. So examples here are going to be lone pairs, which remember are on the central atom, or bonds. But the thing to know about bonds, as you're going to see in the next bullet, double and triple bonds count as one electron domain because it is one area that you're likely to find the electrons. Even though they're in multiple bonds, it's still considered one electron domain. So just reviewing from the last slide again, there are two types of electron domains that exist on atoms. We have what we call the bonded domains, or the electrons in bonds, and lone pairs. And remember, lone pairs only occur on the central atom. So they're only found on the central atom. So these lone pairs are actually going to be repelling more strongly than electrons and bonds, even though they're all made up of electrons. And the reason for that really has to do with what is tethering the electrons. So if we look at our bonds here between the oxygen and hydrogen in these water molecules, the electrons in these bonds are being tethered between the hydrogen and oxygen. And so even though they're being shared, because they're being attracted to two different nuclei, there's not a whole lot of space for them to move around. Whereas when we look at the water molecule, the two lone pairs on the oxygen, these lone pairs here and here are only really being attracted by the oxygen nuclei, the oxygen atom. And so since there's only one thing that's tethering those lone pairs to the molecule, they end up occupying a lot more space. They can kind of move a little bit more freely. And so because they can move a little bit more freely, they can repel more strongly. So they're going to be pushing down on these bonds a little bit stronger than these bonds are going to repel one another. So that's what that's talking about when it says that lone pairs can repel more strongly than the electrons in the bond. So similar to that idea that lone pairs can repel more strongly, what that means overall in the molecule is that they can reduce the angle between atoms. So in the atoms, we can measure the angle between each atom, and so those lone pairs are just going to be able to reduce that angle, make it smaller, because they can repel more strongly. So let's go ahead and start taking a look at some of these molecular geometries that we're responsible for knowing. So the first one is called linear. So when we think of that, right, we're thinking about a line, something that is going to resemble a line. So the molecule we're looking at here is carbon dioxide. And so I've already gone ahead and drawn the Lewis structure for you as to what that molecule would look like. So in order to help us figure out what these geometries are going to be, we're going to be looking at the types of domains that exist. So if we look at the Lewis structure, we're looking for the total number of electron domains. And so remember, electron domains are simply the area we're likely to find an electron, and double and triple bonds still count as a single domain. So in this image here, we have one domain coming from this double bond and a second domain. And remember, those electron domains are always referring to the domains on the central atom. So the total number of electron domains on the central atom in a linear molecule is going to be 2. And of those domains, 2 are bonded and none are lone pairs. And so because they're both bonded, they're going to repel with equal amounts of forces. And if they're repelling each other with equal amounts of forces, we're going to end up having an overall bond angle of 180 degrees. So here's our next molecular shape. It's what we're going to call trigonal planar. So that term trigonal always reminds me of triangle, and planar is going to mean within the same plane. So it's going to be a little bit more flat than another structure we're going to see later on in the video. So the Lewis diagram we're looking at here is for boron trifluoride. And again, the Lewis structure has already been drawn for you. Looking at the number of electron domains we have, we've got 1, 2, 3. So the total number of electron domains is 3. Total number of bonded domains is 3. And we still have no lone pairs on our central atom just yet, but we will see that a little bit later on. So all of the electron domains are the same, which means that they are all repelling each other with the same amount of force. And so if they're repelling each other with the same amount of force, we are going to end up having an overall bond angle of 120 degrees in a trigonal planar molecule. So our next structure is called tetrahedral. So you may remember this prefix tetra from our covalent naming, tetra meaning 4, and we'll see why in just a second. So here we're looking at methane, which remember is the common name for carbon tetrahydride. And you are responsible for knowing that common name of methane. So looking there, again, total number of electron domains, 1, 2, 3. We've got 4 domains here. All 4 of those domains are bonded and none of them are lone pairs. And so you may think, if we were thinking about like a circle, so you may think that in the previous example where we were looking at the trigonal planar, we could take that 360 degrees and divide it by 3, which is how we ended up with the bond angle of 120. But we have to remember that these structures are 3-dimensional. And so if all of the bonds are repelling each other, we're going to end up actually having bond angles that are going to be less than the 90-degree angles that you would probably greater than the 90-degree angles that you probably would have anticipated having, because we are taking up a 3D space. It's not simply 360 divided by 4, because we have to keep in mind the orientation of the bonds in a 3D molecule, which is how we end up with a bond angle a little bit above that 90 degrees, at 109.5. So we've looked at all of our examples where we have all of the bond or the electron domains as bonded domains. Now we're going to look and see what happens when some of those electron domains end up becoming lone pairs. So this first structure we're going to be looking at is called a bent structure, and we're going to be seeing two examples of bent structures in this video. So this is the first one. Here we're looking at a molecule called sulfur dioxide. And the same idea of trying to figure out the electron domains, we're trying to figure out where there are electrons around the central atom. So we've got one domain in this double bond, a second domain in the second double bond, and we have a third domain in that lone pair. So we've got 3 electron domains here. 2 of those domains are bonded, and 1 of the domains is a lone pair. But we have to remember the lone pairs repel a little bit more strongly, which is why we see this larger kind of area that the electrons are occupying. So lone pairs repel more strongly. And so because they repel more strongly, we end up seeing a bond angle similar to what we were seeing with trigonal planar, of it being a little bit less than 120 degrees. So we're going to use water again as our example for our second bent structure. So you go about doing it the same way. You look at all of the electron domains around the central atom. We've got one in this single bond, a second in the second single bond, and then we have 2 sets of lone pairs, and each set of lone pairs counts as its own electron domain. So we have a total of 4 electron domains here, and of those 4, 2 are bonded domains and 2 are lone pairs. And again, the bond angle gets affected because we have these 2 lone pairs here that are going to be repelling more strongly, and so when they repel against the bonds and the bonds repel against each other, we end up having an overall bond angle of about 104.5, which is similar to the bond angle we were seeing in the tetrahedral molecules of being 109.5. So our next structure is what we're going to call trigonal pyramidal. So again, trigonal, thinking kind of like a triangle. And then pyramidal, I want you kind of thinking about it like a pyramid. So in this example here, we're looking at our electron domains. So we've got 1, 2, 3, and then lone pair counts as our 4th electron domain. Of the domains, 3 are bonded and 1 is a lone pair. So in this trigonal pyramidal example, we're taking that idea of having our trigonal planar with our central atom and the 3 surrounding atoms, and now we're going to take it and we're going to pop it up to kind of look like a pyramid where that central atom is going to be at the top, and because it has that lone pair repelling down on all of the other bonds, we end up having it look a little bit more three-dimensional because of this shape similar to a pyramid. And because of that lone pair pushing down on the surrounding atoms, we end up having an overall bond angle of 107 degrees. So what do these geometries tell us? In other words, what are some of the big takeaways from this video? The first one is the idea that lone pairs are going to repel more strongly than bonded domains. The second thing is that the repulsion of the electron domains is what creates different bond angles, and this is where we have that valence shell electron pair repulsion theory that we were talking about earlier in the video. And then lastly, we can predict the 3D geometry of covalent molecules if we understand how to draw their Lewis structure. So we're taking what we learned in the last video and building onto it to predict what 3D geometry we think these different molecules would have.